Hello, and welcome to the 14th clinic in linear algebra. So today we are going to look at what it means for vectors to span a vector space, as well as what it means for vectors to be linearly independent. And so what we want to do is show that these three vectors span R3, right? Well, remember, for vectors to span R3, that means that any arbitrarily chosen vector in R3 can be written as a linear combination of these three vectors. So we want to start by choosing an arbitrary vector in R3. So let's say the vector ABC. Right, so then we want to show there exists constant C1, C2, C3 such that C1U1 plus C2U2 plus C3U3 equals U, right? Let's call this U. Well, what we do, right? Set up the coefficient matrix, yeah? Well, the first column of our coefficient matrix will be the vector U1, won't it? The second column will be the vector U2, right? And then the third column will be the vector U3. We now need the augment, right? So we augment that with U, A, B, and C. So what we want to do is RREF this. With the aid of technology, we can find that the RREF is this. Well, there we go. We have a solution. Right, C1 would equal negative A plus 5B minus 3C, right? C2 would equal negative 3A minus 7B plus 4C. And then finally, C3 would equal negative A plus 2B plus C. So we can therefore conclude that U1, U2, and U3 span R3. So let's find conditions ABC so that the vector V equals ABC is in the span of U1, U2, U3, right? Where U1, U2, and U3 are given here. Okay. Well, to be in the span, so for V to be in the span of U1, U2, U3, there has to exist C1, C2, C3 that are constants, such that V is equal to C1, U1 plus C2, U2 plus C3, U3. So the exact same procedure as we did before. Okay. However, since we're looking for conditions on ABC, we don't want to do this by technology. We actually want to do this by hand. We're going to set up our matrix. And now we're going to start to row reduce this. So this is row equivalent, right? By simply doing -2 row 1 plus row 2 to this. Okay, well, this is going to be row equivalent by doing, I'll do this. -2/3 row 2 plus row 3. To this. Okay, now we can stop. To make things a little bit easier, though, let's go ahead and multiply row 3 by 3. Just to get rid of those fractions. Right. So what we can conclude is that for V to be in the span of U1, U2, U3, right? Look at that last row. This is saying that 0 equals 4A minus 2B plus 3C. So in order to have a solution, right, to this linear system, yeah, we have to have 4A minus 2B plus 3C equal to 0. Thing now, S is a subset of V. Prove that if W is a subspace of V containing S, then the span of S is a subset of W. So let's first take some vectors in S. So let's say that U1, U2, up through UK are within S. Which implies that UI has to be in W for all I, right? Because F is a subset of right, because W contains V, yes, right? Or contains S, yes. So S is a subset. Right, it's right here. All right. W is a subspace of V containing S. Right, so that would be read W contains S, right? Which simply means S is a subset of W. Now, we know that W is a subset of V, which means that for all constants, A1 through AK, we have to have A1U1 plus A2U2 plus so on and so forth plus AKUK. So we have to have their linear combination in W, right? Because W is a subspace, meaning it is closed under addition and multiplication. However, any linear combination of these U's, right, by definition have to be in the span of S. And again, this is true for all constants A1 through AK, right? That is the definition of the span. So every single element or all the linear combinations are in W. I'm saying that backwards. Every linear combination of the U's, right, which are elements of span of F, has to also be in W. So every element of S or every element in the span of S, right, must be in W, which is the definition of a subset. So the span of S is a subset of W. All right, now we're asked to determine if this set of vectors are linearly independent. So recall that to be linearly independent, this system must have only the trivial solution. In other words, they all have to be 0. C1, C2, C3 all must be 0. Well, the easiest way to do this is to set up the coefficient matrix and row reduce it. If you get anything other than the identity matrix, then you cannot have only trivial solution, right? You have non-trivial solution. Well, again, using similar argument, the first column will be U1, second column will be U2, third column will be U3. All right, we now go ahead, RR, EF this, and we'll get 1, 0, 0, oopsie, 0, 1, 0, and then 2, 1, 0. This is not the 3 by 3 identity. This means that this system has a non-trivial solution. And hence, U1, U2, U3 are linearly dependent, meaning that you can write one as a linear combination of the others. What we're now going to do is suppose that the vectors u, v, and w are linearly independent. We will show that u plus v, u minus v, and u minus 2v plus w are also linearly independent. In other words, we want to show that C1 times U plus V plus C2 times U minus V plus C3 times U minus 2V plus W equals 0 has only the trivial solution. So start with expanding this out, right? So C1 times U minus V, U plus V, plus C2 times U minus V, plus C3 times U minus 2V plus W. All right, so group all of the U terms together. I may need to move this down a line. Group all of the V terms together. And then group all of the W terms together, which there's only one. Right? But since we know that UVW are linearly independent. Right? The only way to write 0 as a linear combination is to have trivial solution only. So all the coefficients must simultaneously be 0. So C1 plus C2 plus C3 must be 0. C1 minus C2 minus 2C3 must be 0. And finally, C3 must be 0. Let's solve this system. Okay, so we set up our coefficient matrix, looks like this. Row reduce it. And we get the 3 by 3 identity. This means that C1 equals C2 equals C3 equals 0 is the only solution. So we're done. We must have U plus V, U minus V, U minus 2V plus W are linearly independent, right? We got only trivial solution. Okay. So that is going to do it for today's clinic. In the next clinic, we are going to look at what it means for a set of vectors to form a basis for a vector space, as well as looking at what we mean by the dimension of a vector space. I thank everyone for attending. I thank everyone for watching. I will see everyone next time.